Um,
So here we are back at the Hacking Hours. I'm Jens Petersen, and I'm again joined by Alexandre Marcireau, who I did a pretty poor job of introducing last time. So maybe, Alexandre, you're amazing, and maybe you should have the chance to tell the audience why.
Thanks, Jens. Um, so, just a quick word on my background, perhaps. So, I completed my PhD some 5 years ago now, uh, in Paris, in the lab that spun off Prophecy. So, for a while, I've been sort of in contact with even cameras, in particular Prophecy cameras. And when I was just starting my PhD, uh, Prophecy was being spun off, and thus all the IP, all the code that had been developed in the lab was kind of moving to that structure. Um, so I was told not to contribute too much to the code because the code would move somewhere else. Um, and since I quite like developing stuff, and since I did not want my PhD to rely on closed source code, I decided to start rolling out my own framework, by lack of a better term, some piece of code that would let me load events from a neuromorphic camera, do some processing, some display, that sort of stuff. Um, and that became an integral part of my PhD. And since the end of my PhD, I've been a postdoc at the International Center for Neuromorphic Systems in Western Sydney. Um, and I've kept doing some of that. So I've reinvented the wheel multiple times and developed way too many frameworks. Is a way too generic a term to really be precise, but overall tools to help me process, make sense of, or represent the data coming from a neuromorphic camera. And since Jens is developing some of those things as well, when we met in Telluride a couple of months ago, we really decided to try and work together um, on, well, what is currently called Faery. But it's really more, I think, of a broader effort of trying to de unfragment
Hmm.
the ecosystem.
Defragmentation. I like that word. Yeah. No, I think it's just good to know the background. Also, that you've been massively active in the open source community, right? So a lot of the tooling and software around event cameras are, thanks to you, which is absolutely amazing. And it's at some point I saw someone trying to calculate the value of NumPy in monetary terms, how many
Oh,
companies are relying on NumPy. I'm not saying your software is exactly
not
NumPy
quite.
yet. It will be, right, but if we would be if we would be rewarded based on the number of users, I think you'd be a rich fellow. But I think there's just something to be said about the amount of effort you've put into this, which is fantastic. Yeah, and we're back at Ferry, and you mentioned something you've been working on since last time. Yeah. Maybe we
Yes.
should we maybe start up a virtual session again in Visual Studio Code? Um,
Oh, that's not a bad idea.
just then I
Um,
can just follow your screen.
mhm. uh,
And then at some point we will also be joined by Petruț Bogdan from Innatera, who said he would grace us with his presence. But I'm actually looking forward to that conversation. I think it'd be fun to maybe um, see what you guys think of each other and maybe talk a bit about other open source neuromorphic tech. Do you know the Innatera company actually, Alexander?
um, by name only. I've heard that name before, but I'm not familiar with what they do.
So without spoiling too much, I think it's fair to say that
Mhm.
they build chips, and it's one of the chip manufacturers that's managed to build a mixed signal processor
All right.
into commercial, which I think a lot of people are curious about because that's not something we see every day. Um, so I'm keen to also talk to him about something like the neuromorphic intermediate representation, which I admittedly have a bit of a
Oh,
stake
yeah.
in. But for me, what really matters, what would be fun to talk about, is some of the interoperability. I mean, what you also mentioned, right? Essentially, a way to defragment that um, ecosystem, because it is indeed very fragmented, at
Mhm.
least as far as I can tell. This is now the link I copied in from your message. Thank you for sending it.
Mhm.
And I think once it's starting to follow, I can just follow your cursor around, so you can share all the details with it. This just works. That's amazing. I can now see your cursor in project scripts. Fantastic.
That is nice. 45. Oh, yes, that works. Excellent. Um, okay, so just a quick word on. So I've changed two things mostly.
Mm-hmm.
Some of it has to do with low-level reimplementations. For instance, I moved the CSV parser to Rust to make it much, much faster
Ooh, nice.
with the Python interface, that sort of stuff. So that is interesting if you care about Rust and low-level programming. But otherwise, it's almost a technical detail hidden deep inside the system, right? And I've also made small changes to the user-facing interface, which I think are more interesting and kind of also create the puzzle in terms of types that I'm about to describe. So I might actually start with this, which is, at least in my head, the ideal user-facing interface.
Hmm.
That's what I'd like us to get to, where you have different functions to create a stream, and that can
Mm-hmm.
be long-term from a camera directly or from a UDP source and so on. Um, and then a series of filters. And what we really want is for Python to know what's available, right? So when you press dot, you get a list of all the functions
That
you
would
could
be
apply
awesome.
to your
Yeah.
stream. So say I want to crop it, which is what I was doing here. So we'll have a crop. And then after cropping, which is a spatial, there we go, spatial operation, I could also crop that in time. So slice a specific range of data, perhaps because I want to do a slow motion render of that particular range of data. Um, so something that's kind of interesting, I think, is that if I hover in VS Code over the different functions here, it tells me that this is a finite event stream. Finite
I
event
I
stream is a
actually don't
stream with,
see that. Maybe I
oh, you
can.
don't. You
Maybe
may
I
have
can.
to do the same thing. So if you
There we
go
go.
to
Yeah. So now I'm hovering over time
excellent,
slice, and it says finite event stream. So that's a specific type of event stream. It's not just any event stream, right?
absolutely. And the key idea here is that the type of event stream tells you what's possible or not on a particular stream.
Yeah.
For instance, because this stream is finite, I could feasibly turn it into one big NumPy array. I could collect all the events, wait for the stream to finish, and have one big array. It's usually not something you'd want to do on, say, a very large file, because at some point the memory is going to blow up. But it can be insanely convenient if you know for a fact that you're working with a file that's small enough to fit in your memory. You can have just one big array and then go to town
Hmm.
on that array and do whatever you want with it. However, if you're reading data from, say, a camera, you wouldn't be able to do that, right?
No,
So two
because it's not
array,
finite, right? It's clearly infinite. Yeah.
exactly. And that would give me an NumPy array. So what I could feasibly do, for instance, is call that events. And that could be part of a bigger script where I'm really just using Faery as a way to load the events, crop them, select a particular range, and then the rest is up to me. I can implement my own, say, tracking algorithm, for instance, from that point on without leaving the Python ecosystem. Makes it nice and flexible.
That is
Uh,
super nice, right? Yeah.
so I could do whatever I want with events here. And then, for instance, I could do Faery dot event stream from array with those events as the input. And I think that I need a couple of other things. Oh, the dimensions as well, because otherwise Faery doesn't know. Uh, so that's going to depend on my camera, and that's something that I could feasibly read from the stream here before converting to an array. Um, and then now that I've done that, I'm back to having an even stream. So I can now save to a CSV file, for instance, that sort of stuff. But the idea really is that you can move out of the sort of streaming pipeline into static arrays and back to streaming pipelines if you want to, that sort of stuff.
Amazing. Yeah. And like you say, it's
I guess
entirely in Python, right? So it's very, very scriptable,
it,
essentially, right?
absolutely, that's really the goal, to have that sort of flexibility. So sort of natural to extend, with, of course, support for all the types. So you can just read from the .ts
I
file,
love
.adat,
this. Yeah,
whatever.
exactly.
So that's really the goal, to be. So really in scope, the library isn't that big, right? It's not trying to have all the denoisers in the world. It's not trying to have like massive backpropagation built in. It's really meant as something that does quite a that is unintrusive but does quite a lot in its flexibility, in a sense. Um, okay, so that's the goal. How do we turn this into something that actually works, right?
Can I make one comment
Um,
though? I mean, because I
uh-huh,
think
yeah,
we had one earlier file name that we called, I think, read or from stream or something. What was it? I called it events
yes.
input, which is
I've moved some of that out just to whilst I was merging everything, but happy to put it back. But I think that it's not strictly needed.
no, no.
Um,
In principle, I think
if
it's
we
I
have,
like this because it's very clear. I just wonder whether we should call it if I mean this is nitpicking, right? I wonder whether we should call it events from array. But I guess what you're trying to hear, you're saying you get a specific event stream, right?
so the idea is that at some point we may want to have, say, a frame stream from file, for instance, where you're reloading a stream of images.
I
Um,
like that a
so
lot.
so this
But
is the idea that this is a stream from an array, and the type of the stream is events. It's not an event stream; it's an events stream. Mostly because we're moving around packets of events. Each packet, each item in the stream is really a NumPy array, which is ugly from a conceptual perspective, but it's so much faster.
that actually makes sense. I can see we're joined by Peter. Hello, Peter.
Hello, I'm sorry. If you're streaming or recording this, I just messed up the where you frame each of our faces. But hello, nice to meet you, Alexander.
Nice to meet you too.
I think it should be focusing actually, which it isn't. I mean, the whole point of this is to learn as we go, right? We're none of us is like expert streamers, so the audience will have to suffer that. Although I can see you have an incredible camera mount, right, or microphone mount right there, Peter. That's pretty impressive.
Thank you. I'm here for the SMR. It's
Um,
really important in those meetings where people are really synesthetic. They need to see the colors, they need to see the mic. Or it's for me. I don't know.
I mean, I'm just starting now to grok what is happening in your background. You have all sorts of awesome balloons and colors. It's absolutely. I mean, I'm completely falling behind here, Peter. Is it your birthday? I should have brought you a present.
Thank you. It's
but
for my 30th birthday. Yeah.
really, whoa, dude, congratulations! You're halfway 60. But that's a milestone, you know. But what I wanted to say was that now we've slowly working a bit on Faery, and maybe if you don't mind, Peter, we can do that for another for a while until we kind of talked about one issue here, and then I'd love to get you in. But maybe before we jump to a different topic, or we continue working, Peter, I wonder whether you can say a few words about you. So I put Alexander in the spotlight similarly, but you have also done awesome work, and you've also done awesome open source work. So I wonder whether you can just say a few words about who you are and why you are here.
Is this one of those speed dating questions where you don't want me to talk about what I do for work, or is that something that's okay? Is it who I am as a person, or what I represent on the outside world?
It's the inclusive kind, so you should do whatever makes you feel comfortable, whatever you want to talk about.
Sure. Okay. So I'm a Romanian guy. Peter is not my real name. I go by Petruț in Romanian circles, but for most other people, Peter is good enough. My name translates to Little Peter. And for those who realize I'm almost 2 meters, that is a fantastic joke that my parents played on me.
Thanks, parents.
I left Romania when I became an adult and went to the UK instead. and went to Manchester to do my bachelor's and my PhD and my postdoc. I started working, I think after my first year of bachelor's, I started working with Spinnaker because I just happened to be there. So I worked as a verification engineer for what became known as the Spinnaker software tools. So that's the open source bit.
The Spinnaker with a Y, right? Very apt naming scheme you had there. Yeah.
Yes. It stuck, I think. I mean, it's still there. The publication's doing well. It's related to Pine. It's a Pine front end. It's a Pine back end for Spinnaker. So that was that bit. I did my undergraduate project also with Spinnaker, where I did a robotic art installation at the Manchester Art Gallery, where I controlled a couple of robotic arms using Nengo running on top of Spinnaker. Which was a lot of effort for a poor PhD student who had to do all of that porting, because I didn't have to do that. I was a user because I was still an undergraduate and therefore didn't know much about what I was doing. Then I did my PhD, which involved a loftier goal to begin with. I wanted to study neurogenesis and self-organizing systems on Spinnaker itself, less on the developmental side, but more on the adult neurogenesis type of modeling. Jens.
Very cool. No, well, so I think this is a wonderful portrayal of you, and I wonder how that landed. No, no. I mean, at some point, Peter, we should do like a whole feature of you, like, because that would be fun. But I mean, like, you landed in a I mean, so you've developed a lot of software for Spinnaker, which has been used by a lot of neuromorphic researchers. But you landed in a company that builds that actually tries to bring neuromorphic hardware to the masses, right? Did you bring a chip? Oh, amazing.
So did you ask for a chip? Okay, let me see what I can do.
Well, I mean, I'm asking why you went away from the camera and picked something up. Maybe
no,
it could
that is
be
correct.
another
I
birthday
did,
sigh. I don't know.
Okay, calm down for a second. So I need to zoom in, and that's the wrong zoom in location. So I need to zoom in on my chest. That's a good enough zoom in. Maybe I can. So. And does my camera work? Is this okay? Let me zoom in a bit more.
That's a Spinnaker chip, isn't it?
That is a Spinnaker chip, but
that's
I need
amazing.
it for scale.
It's a little, yeah. That was better. That's better. I think it's much more in focus. Yeah. Okay. That's a Spinnaker chip. That's amazing.
But I probably should turn out the pinkish hue behind it. So this is Spinnaker. I also happen to have in my collection a spiky.
Oh God.
This is difficult to hold.
That's like an order of magnitude smaller. That's crazy.
So this is a spiky. And you can also see so if I tilt it just the right way, can you see the crossbar arrays on the spiky chip? This is a brain scales chip.
We totally can. Yeah.
Yeah.
What's the pitch between the connectors on the spiky? How do you bond it to a PCB? How do you bind it to a PCB?
It's not my chip. I don't know.
So Spiky is the brain scales project from Heidelberg, right? Is that correct?
So, yes, this is a analog mixed signal first generation or something, very early generation from the Heidelberg University, from the brain scales group. And I don't have details about packaging. I don't know how it's mounted to a board. How you're supposed to use it. They've done their own magic, and I don't know. Sorry, that information we can direct. We know people who know this kind of information, and I'm not one of those people.
We should invite them to a hacking hour at some point. But I guess that's then that's then yours. Okay.
This is the Hyken DLS. This is still brain scales, so they've gone a bit larger in size. And I can't hold mine because it's this. I'm gonna drop it, and I'm sorry. So it's this. Is it light? Where? Can you see the speck of?
We see a tiny grain of sand between two.
It's very difficult for me to hold. Okay.
Yeah, so, I can see. But it's also what's the dimensions? Like 0.5 millimeter or something?
No, it's more like 3, but the spiky is larger than that. So this is a spiky, and I can hold it nicely, and it doesn't drop out of my hand. But I can't do the same
That's
without you.
fantastic.
This is the first time I do it on camera, so.
Okay, Peter, that is really cool.
I can almost do it. Okay, so very tiny.
This is a great teaser, I would say. I mean, I still would like to maybe come back to this a bit later, because then we can also talk about something you and I, Peter, have been talked about, which is the neumorphic intermediate representation. Ooh, that's the demo. Whoa! So this is the radar demo. Is that correct?
No, this has an infrared sensor.
Infrared.
But
right.
but yes, this one has a few other sensors on the development kit as well. The chip doesn't care, but the chip is somewhere in the middle of this 3D stack that I can't easily disembowel at the moment because it has screws, and I don't have a screwdriver because I am a software engineer.
You just show off like other people's hardware, basically. No, but okay, so this is an amazing introduction, I think. But I wonder whether we can pause that for a little bit, because I actually feel I get completely lost in this. I want to ask a ton of questions, and if I do that, then I worry that we won't ever fix Faery. Alexandre, would you be happy to continue working on that for a little bit?
Yeah, of course, absolutely.
Peter, do you know what Faery is?
No.
Ooh. So check this out, for instance. This is a wonderful example that Alexandre just gave, where we can take some of Alexandre's wits and experience to, for instance, read complicated event files, which is, for those of you who don't know, been a huge problem in the literature, because it's just very hard. So the challenge, of course, is to do that in a nice API so you can do different things. And of course, ideally also work with event cameras and stream to GPUs and so on and so forth. And now I think we're talking a bit about how to construct an API that can do this adequately in this new library called Faery, which is obviously a pun on address event representations and fairies, because you fairy thing from A to B, right? Maybe.
Okay. Very good. Very good.
Also a reference to image magic. So it's not wizard, it's a fairy. Close enough.
That's a really good point. Yeah, we should have that mascot everywhere on all our wizards, basically. Yeah. Anyway.
But yeah, the idea is really to build for events something that is a little like pillow or pill for regular images. So something relatively low level whose primary job is to load stuff and write stuff, and then some minimal basic operations in the middle. So the goal is not to build OpenCV for events or TensorFlow, but something smaller than that, like Image Magic or Sharp or Pill.
Okay. Could I ask an unrelated question, just organizationally? I forgot to ask about it earlier. Jens, are you streaming this?
I'm recording, at least, which means that at some point I might consider uploading it to YouTube, but I'm not streaming it yet.
Do you want me to stream it?
Yeah, sure. I mean, I uploaded to a channel afterwards, but I mean, this is supposed to be as open as possible. I just haven't bothered to find out exactly how to.
This is not gonna work. This is not gonna work. Okay, I interrupted this for nothing.
No,
this
please.
Is gonna be very difficult. Never mind.
Let's pick this up afterwards. I'm sure I could learn a few things from you. Sorry, Alexandre.
Not at all.
Okay. Faery is a software package that's supposed to Faery address event representation events from A to B while also doing some minimal preprocessing to them.
That is exactly correct.
And it's mostly AR streaming for vision-based applications, because you're
very much so
into OpenCV.
But I guess in principle you could do any AR data. Right, but sorry, go ahead.
Okay. In practice, at least for the first version, it's going to be DVS like events. So polarity can be on or off, and you get an X or Y and a timestamp, and that's it.
Okay, very good. How does this build on top of AES Stream, the work that you had in the past, Jens, or is this a
I think
extension?
it's fair to say it's a combination of efforts. So I think some of the things I would love to do, for instance, is to stream stuff onto GPU, because I'm a heretic, and I'm waiting for the perfect neuromorphic platform at some point. So I think that work we can borrow from AStream. But I think actually this is mostly the Faery initiative was actually started by Alexandre. So I think
Yeah,
it's spiritually similar. Is that fair to say?
yeah, absolutely. Likewise, it's conceptually inspired by some of the stuff I've written in the past, but in terms of code base, we've started from zero again, partly so that we can build what we have in mind get to the point where ideally we can have a zero dependency or almost zero dependency Python package.
Good luck with that.
I know.
We're almost there, actually.
It's only NumPy.
On an NumPy and PyTest as well, I think, and maybe something for the command line interface. It blows up quickly, doesn't it?
Well, I mean, PyTest you can wait for the testing, right? But yeah, that's a fair point. Anyway.
Okay, so this is the goal. That's the target API. With ideally static typing, so we want the user to automatically have a list of all the functions that they can reasonably call on a stream as they're assembling different filters. And those filters need to be aware of the nature of the stream, because some operations, say for instance, generating a figure that represents the event rate, only make sense if the stream is finite. There are also operations like converting to frames that are far easier to implement if the stream is prearranged into packets of equal duration, that you can apply the operation in a more seamless way. You have to stitch together buffers to cover the right amount of time and so on. So in terms of stream types, at least at the moment, we really have three-ish. Well, four technically, but the fourth one is an assembly of two other types. So a regular stream, which is potentially infinite, and each packet gives you no guarantee as to how many events are in the packet. Could be one, could be 10,000, could be zero, and no guarantee in terms of the amount of time covered by the events. Like it could cover 500 microseconds or 10 milliseconds, and that can change from packet to packet. Then the finite stream, which is the same thing, but
Sorry, could I just ask a quick question? Because in this packet structure, if you have multiple events, are they ordered by priority, or is there a timestamp associated with each event, or does it not matter?
That's a good question. Timestamp. So events have a timestamp encoded throughout the library on 64 bits. So even with microseconds, we've got plenty of microseconds to go. And the library guarantees, if everything goes well at least, that time is monotonic, always going up.
Is maybe my understanding is slightly wrong. I'm just trying to map it a bit to what I expect a bit from a physical DVS camera. Is it guaranteed that it always comes with a time step? If it streams out events, is it guaranteed that there's going to be a timestamp associated with each event?
It depends on the level at which you're taking the DVS outputs. So our target is clearly a computer sitting behind a USB port, and every neuromorphic USB camera has a timestamping system before you reach the USB packets, mostly because USB is not real time. Technically, if you're working, well, not real time in the sense of gives you no guarantee in terms of latency and jitter and so on.
Right.
If you're working with very low level silicon, you could remove the part that timestamps the events and work directly behind the arbiter. And if your system is properly real time, like say a brain, in the sense that different pathways can have a set duration. I think that you can remove timestamps altogether. In a sense, every neuron gets access to this variable, which is time for free, everywhere, all the time. But we're emulating that with timestamps.
Right. But I meant as a generalization, once you so also trying to understand a bit the scope of the package, whether it's likely for it to be implemented in sort of bare bones or bare metal or almost bare metal microcontroller, whether that's part of the how you're envisaging it. Because I mean, sure, all of it is in Python right now, but it could be written as a pure C or Fortran or some other highly optimized bit of code to be able to run in those scenarios. And there, I would expect that you'd want the DVS to use as little power as possible and therefore not assemble any time steps, simply stream events as they're happening. And you don't want to do any buffering or time stepping at the receiving end, because you should be able to just process spikes as they're coming in.
That is a very, very good point. I think that the answer, at least from my perspective, but Jens, please jump in if you have a completely different vision, is no at the moment. So the goal is not for it to be implemented on very low-end hardware. It's really meant to stay on your CPU to help you manipulate even files. So really as an algorithm designer rather than a hardware designer or someone working on a hardware implementation or close to silicon implementation of the code. Mostly because, at least in my experience, when you're doing that, you typically throw away any sort of framework that you might have because you're trying to optimize for everything. So unless that framework is already fine-tuned for that particular piece of hardware, usually it gets in the way. And getting rid of it lets you optimize further down.
I would totally agree with that. I just want to add one thing, which is that it's technically now is generic, right? So we could extend it if we want later. But I totally agree. Like, I think now we just try to solve one specific problem and then maybe extend it in the future. Sorry, I interrupted you, Peter.
No, it's all good. I mean, we're doing this online. It's difficult to find timing. I don't know where everyone is. I'm guessing you're in Sweden and Denmark.
I'm actually in Copenhagen at the moment.
Yes.
In the Botanical Gardens, where they set up an AI center, which I can recommend checking out. All right, you should come visit.
But I think that the additional important bit that I wanted to say is that sometimes you need to throw away the framework, but sometimes you also need to think about who your user, or in our case, the customer is, and what their desire is, because one end is pure performance and how much can you squeeze from a bit of hardware, from a system, from whatever. At least for us, it's also very important that you make a usable system, something that is easy for someone to pick up and to be able to quickly reconfigure and do something slightly different or completely different. And it's always a spectrum. It's always a trade-off that you can do there. Anyway.
Okay, that makes a lot of sense.
Yeah, I mean, spoken like a true developer, right? We have to watch out of feature creep. But you were walking us through the event streams here, right? So now we looked at the finite stream.
Mm-hmm. Okay, so the third time is the uniform stream, which is potentially infinite, but packets now come with a new guarantee that there's always the same amount of time per packet. So each packet is a frame, if you will. You're still carrying events. You can have multiple events per pixel, so it's the same format fundamentally. It's still a list of timestamp X, Y, and polarity. But you are now guaranteed that if it's packet 0 and your period is 100 microseconds, every event with timestamp from 0 to 99 is going to be in that one packet, still in order. And the next packet is going to have everything from 100 to 199 and so on and so forth. That typically doesn't come that way either from a camera or from a file. If you're reading a set number of bytes per iteration, you will, from most formats at least, get a variable number of events and a variable amount of time. But if you're planning to resynchronize streams, if you're planning to turn them into frames, having that guarantee opens all sorts of doors in terms of facility of implementation.
So, but I mean, what I'm hearing you say is that you have a starting point and an ending point in time, and everything in between there is what you get, like no matter whether there's 0 or 1 million events, basically, right?
Yeah. So variable
would it
number
be
of events.
fair to say, like, call it an interval stream? Like, because uniform, I guess, comes from the fact that it's like uniform in time.
Yes, I took it from uniform sampling, but I'm happy to change its name. I'm not 100% happy with the name. I just couldn't think of one that didn't feel potentially confusing for other reasons. But if you like, actually, interval would be much better. More than happy to go with that.
I
Had
mean,
any
it's
strong
also not
feelings
something we
about
have
the name.
to go into now. But I mean, uniform can also have like a spatial meaning. But I like that.
Sure.
I think there's a crucial distinction between having just like a finite stream and then this finite stream which has like packets of a certain size, right?
So there is a variant of this thing, which is a set number of events per packet. But at least from my perspective, it's no different from a regular stream. Even if you know that there's always going to be 1,000 events, typically the sort of operations you can carry out on that structure is really similar.
Yeah.
And then the finite uniform stream, which is a uniform stream that happens to have a begin and an end. And that lets you potentially do everything you can do with a finite stream, or everything that you can do with a uniform stream, or maybe things that you can only do on a finite uniform stream. I haven't found anything yet that only applies to finite uniform stream, but I'm sure that we'll find something at some point. Okay, and then some utility classes that just define filters, filter being like a stream except that it has a parent, and thus will pull data from its parent rather than pulling up from thin air, which is what file reader does. But those are really just similar things. I mean, similar concepts, just something that has a parent. Okay, so those are our 4 types. And the whole idea is that whenever I'm writing functions, implicitly, the very first input, my entry point, will implicitly, depending on the type of things I'm reading from, say a file versus a UDP socket, be either finite or infinite, or perhaps even uniform. So it has that kind of type built in. So for instance, when I'm reading from a file, I get a finite event stream. And when I apply filters, I need to carry with me that information to know which filters I can chain on that object. And where it gets tricky is that some of the filters can change the type. For instance, if I call the dot uniformize, which we may want to change if we change the name uniform, on this with a set period of say 1,000, I now have a finite uniform stream. It's finite because it came from a finite stream and I'm uniformizing it. But if it came from a non-finite stream, a regular or infinite stream, then I would get a uniform stream, but not a finite uniform stream, if that makes any sense.
Yeah.
So it gives us a power of composition by just carrying that information through the types whilst you build your pipeline. It's worth mentioning at this point that those little pipelines don't actually do anything yet. What does something is the very last operator. So when I call save will iterate over the events of its parent, which in turn will iterate over the events of its parent, and so on and so forth. And they will all apply their operations on one packet at a time, and then I'm saving that packet and going to the next packet. Lets us do things without loading too much memory. Also means that really the pipeline itself is more of a configuration class, a configuration object, rather than actually performing any operations, which means that you can easily copy them. So you could, for instance, have A here that is non-uniform if I wanted to get a sense of the difference between uniform and non-uniform. And then I could do A.save and then A.uniformize.save. Where
Nice.
I would be reusing the definition of the first pipeline twice, I would really be reading the events twice. But I think that sort of thing is relatively good in Python in that that's the sort of stuff that users, voluntarily or not, will end up doing. So having support for it is quite nice. And it really lets you recycle pipelines in a relatively neat way. It's going to be slow because you're reading the events multiple times, but at least in a scenario where you're doing some post-processing, it's not a major issue if it's a little slower if you're doing some of the things multiple times, I think.
I really like this, but I mean, was there a dilemma somewhere in here? Like you mentioned all the typing, that must be difficult to kind of stitch together.
Yes. So where did I write my little rent? Oh, there we go.
It's always the kind of comments you love finding in someone's source code, right?
I don't know. Where it's like, okay, someone felt like the source code needed this amount of stuff just to
I
justify its
remember there's
existence.
one really cool comment. Isn't it in the Linux source code somewhere, which says like talks about how difficult a problem this is, and then at the end you can increment the counter of how many hours are wasted in this line of code with how many hours you wasted. And then eventually, as the code grows, it becomes. We should totally have that. Anyway.
I quite like that. So the beginning of this little rant here starts with the description of those four filter types that we'd like to support. And then two of the goals. So one of them is, or perhaps before I go there, a few examples of filters that are important. So if we look at crop, for instance, just select a rectangular area in your video stream. That's something that's available for every single stream type. All crop needs to do is make sure that whatever comes out is the same stream type, uniform, finite, uniform, and so on, as the input, because it doesn't touch that. If it was finite before, if you're cropping, you're still working with a finite stream. Then we have functions that are only available for certain stream types, like toArray that I've mentioned before. And then we have functions that change the stream type. Uniformize, for instance, which makes a stream uniform. There's also a function that chunks your stream into a set number of events, and that actually destroys the uniform property. If you're saying I want exactly 1,000 events per packet, something that was uniform is not uniform anymore.
Yeah.
So you've got those different cases. And it is important that we preserve that type information to make sure that, to make sure that the users knows what sort of event they can use. Importantly, in some cases, uniformize, for instance, the actual implementation depends on the type. And that is because if you're reuniformizing a readily uniform stream, in some cases, let's see, how did I? Oh yeah, so it had to do with I wanted to drop entire packets or not at all. I think it felt like it would make more sense, which perhaps it doesn't. Was it? Sorry, I've lost my train of thought.
All good.
I'm pretty sure that there are a few edge cases where, for certain stream types, it felt more natural to do one thing rather than another in terms of where exactly you cut, because you've got all sorts of possible options. Say if your uniform stream, oh no, sorry, it wasn't in uniformize, it was actually in time slice. If you're slicing a stream, say your stream was going from 0 to 10 seconds, and you're saying, I want to now go from 0.5 seconds to 9.5. If you have a uniform stream where each packet covers 1 second, you have to make a decision. Do you reshuffle all the packets because now you're starting from 0.5 to 1.5? Or do you drop the entire first packet? So now you're actually starting at 1 second. Or do you keep the entire first packet even though the user said, I want to start at 0.5? You're like, well, to do that, I need to include the earlier part of the packet, that sort of stuff. I don't know if I made the right decision. I just want to point out that for some filters, you do have that extra bit of flexibility, or possibly slightly different behaviors depending on the stream type. Okay, so
Could I ask a quick question?
uh-huh.
I mean, it might not be a quick question. Why am I assuming? Um, I'm trying to understand where some of the implementations that you've decided on, um, where the idea for them came from, or what problem they're solving. Is it do you already also have some sort of use cases in mind that you're trying to optimize with some of these decisions, or are you trying to preempt what you expect are operations that an engineer would maybe want to use in the future? Because I can think of a lot of I can think of some benefits of having a packet of uniform size, for example. I can also think of drawbacks. I can think of infinite time waiting for the event to pop up for you to send that packet with 999 events in it. But I can also think that in terms of processing, you can set up a pipeline or a FPGA or whatever device that can do a certain level of processing with a fixed batch size, let's say. And for like a server type operation, you could optimize the operations that you're doing on that data. But what kind of applications are you looking at that are grounding some of your decisions?
That is a very good question. So when it comes to non-uniform packets, Faery is really a follow-up to another library that I wrote, that was really kind of a weekend side project idea that turned out to be far more useful than a framework I spent an entire year designing. And it was really just a very simple Python script that would just take a directory full of event recordings, which is something my lab does quite a lot, and turn that into videos. And then a bunch of options and some sort of configuration file in the mix that would let you select a small range in that file. And as that project grew more complex with more requirements and so on, it became clear that the configuration file in TOML was not helpful enough, and I ended up like implementing something that felt like templates, and I was this close to reinventing the for loop, and realized that actually an
God.
actual programming language was much better, right? Like if you're writing a little script where you're specifying what you're doing in different files and so on. I was working around not having a Python API, but really I want a Python API. So a lot of the decisions made in Faery are really just me implementing that sort of concept. But after chatting with Jens, who does a lot of his processing on GPUs rather than CPUs, he mentioned that typically having a frame of events is something that comes relatively naturally into play. I made the assumption that that meant a fixed amount of time, but that could be very wrong. That said, that fixed amount of time frame is also very useful whenever you're doing rendering, which is really the action of turning the events into a frame where you already have all the events in a file. So there's not going to be any waiting. If you reach the end of the file and you haven't covered the full second, you just say, well, my last frame is going to be slightly shorter. Who cares? And render that anyway. So it's in that context that I'm trying to make some of those decisions. That says there's a fair bit of guesswork of, okay, I don't have that use case quite right now, so I'm just going to assume something, which is why I haven't spent, perhaps already spent too much time on something for which I don't have a clear use case yet, but haven't really dedicated all that much time to it because I figured, well, let's just implement one way of doing it. If people like it, great. If they don't, and they have a clear reason why they don't, we can sort of workshop that, improve it.
Right, all this makes sense, yeah.
And I really like also the consideration with the history while also balancing, getting something out, right? That's always the trade-off, right? It's fun to sit and design all these things, but it's really, I mean, apart from the fact that we're actually struggling with some quite hard engineering problems, right? It's also a matter of building something that can work, like, and help us or you tomorrow, right? Ideally. Yeah, I didn't mean to interject, but I just want to comment on the solution here, which I find really beautiful, because here you're kind of delegating the responsibility of what a given filter would support to the filter. Right? The filter has to declare, okay, if I have a uniformized filter, right, this only works for uniform or finite uniform streams. Right. Which I think is a very nice. I mean, it's almost close to the template, except it's not programmatic, right? You just have to hard code the fact that this works
Yeah.
here and it works here. It doesn't work anywhere else.
So this is the part that I'm sort of okay with, but not 100% happy with yet. And really comes to the fact that this is very dynamic. So what you're looking at right now is effectively a for loop at runtime,
Yeah.
because Python doesn't let you do that before running, which is fine. It just means that your static typing system doesn't know that. It doesn't know that there's going to be a class called uniform something at runtime, because that class doesn't exist yet. And as a result, the script can run, but it can't tell you what's possible and what's not possible, at least if it was just that. Hence the other file, which is the eventstream.py file, the one with the big chunk of green text. And that one has, sadly, explicit classes for all the cases with all the functions and the signatures. It's just that those functions don't have anything inside them, because that's in the other file. And then there's just a little for loop that binds them together. So that's kind of a
But wouldn't
rig.
this normally be in a what is it, the PIY Python interface file?
That would work too, yes. We could also make it an interface file, which is really the same thing. You would also, unless those files support for loops, but I don't think that they do. I could be wrong.
I'm not no I don't think they do, but I mean maybe it will help just distinguishing what is actually code and what's kind of a boilerplate interface kind of thing.
I like that actually. That yes, we could absolutely move it
Because
to
this is, as far as
UI.
I can see, this is purely type help, right? This is purely for the type checker to make sure that.
Sort of. So there's one last subtlety, which is that all the classes in the other file need to be instances of this class to have this chaining thing. But that class cannot know about those classes yet. Otherwise, you get an infinite loop of imports.
Yep,
So
that's bad.
there's yet another trick where the import happens if you scroll down to line 559.
Can I follow you again, maybe? There we go.
So this is how we avoid the for loop. So really, you import even filter, we import even stream, because every filter is inherits from something defined in stream. It needs to be a stream because we want to chain. So it needs to have all the methods that you could chain after calling that one, the one that returns this. But in stream, we also need the implementation of those classes. So we also want to import events filter in stream, which would create an infinite loop unless you do the import inside each function. That way, as the first pass, when the Python interpreter is reading the file, you get the first import, which is not infinite yet. And the one that would close that infinite loop is hidden inside the function. But once that happens, everything has been loaded already, and Python is fine with that. So it is what it is. I'm not terribly happy with it, but that's Python, so some things bound to be a little ugly, I guess.
I think the reason why it's particularly problematic is because random people who will want to write filters, right, will make that mistake and get to infinite loops, right?
So I thought about that.
Ooh.
So, well, to some extent. So the idea, I think, is that unless someone is writing specifically for the library, where we want to support all use cases, there's a good chance that they'll want to support only a subset of filter types. sorry, stream types. Say they are working
Yeah.
on,
Yeah.
unless it's really an extension of the library, they're probably, say, working on files. And all they want to do is implement their, say, tracker, because they are writing a paper on a new kind of tracker,
Yeah.
and they want to process example files to show how it works.
Yeah.
So typically, they would only need to support not all filter type, all stream types, just one stream type, which is what apply is for. So apply just takes any filter type that is derived specifically from infinite for an infinite stream, or finite, which is actually a mistake. That should say finite even filter, finite even filter, and so on. I'll make sure that I didn't make the same mistake elsewhere. So the user can just write one class rather than a generic class, and then call the apply function. So that lets us bypass those two issues, so the infinite loop and the generic weird stuff, by just having something that is defined completely outside the library and isn't statically available. So it's not like they're going to have, otherwise
Yeah.
somehow statically, say, if I'm a user and I'm creating a new filter, denoise, for a user to somehow be able to do this, to have
Yeah.
denoise as if it was part of the core library, they would need to somehow register it, because they're not modifying the source code of the library, right?
Yeah.
Except that if they're doing some dynamic registration, then it cannot possibly be statically typed, which means that this cannot work. What can work, however, is apply denoiser, where denoiser would be some sort of class that I'm defining here.
That is a really, really good point, because then you can just use it directly. Okay, actually,
Yeah, that's kind of the idea.
I kind of like this. I mean, as you said, I don't think it's flawless, because it is a bit of a hack. But I mean, to get typed information, this is great. And then it might make sense to look towards what the PIY files actually can do and can support. Maybe just to disentangle, right, the logic from the interfacing. But otherwise, I mean, I think this is it. Having a type hints would be a tremendous help, at least for me.
Yeah,
I think.
So that's kind of the current thing. I thought of a few other things, or tried a few other things that did not work.
Did it work with templates?
So that's an option, right? To write the code once and then automatically generate all those possibilities. But I feel like that's also not ideal, because it means that you're now not writing quite Python. So for a library maintainer, decorators are probably less bad than a completely new template language.
Yeah, for sure. I like the approach now, because it seems like it's viable for now. And I think it's really helpful you wrote down the other options, because then we can see whether there's something to be inspired from, right?
So it's worth mentioning that the example is not just an example. This is actually already working.
That is so cool. This is really nice. So you can crop, time slice, and save. And you could, in principle, also save not as a CSV, but as a dat, right? Technically.
Absolutely. Yep.
Or as a Petruț, new file format, or event stream, who some clever person invented, I heard. Right.
So that part is written in Rust, and that is in SRC here on the left. So for now we have support for ADAT, CSV, DAT, event stream, and EVT. But the idea is to have as many as we can. It's a fair bit of work to add new formats, because it's not pure Python if we want it to be fast.
Yeah.
But to me, that's really one of the core goals, if not the most important goal of the library. That. So
yeah, that we join forces, right? That we can use one set of decoders and encoders instead of having 10 libraries that do the same things.
Yeah, what does not work yet, but that I really want to get to, would be to say, let's pretend that I'm using 60 frames per second. So I'm going to uniformize at 0.167, I think. And then render, which doesn't exist yet either, but would essentially take those slices, turn them into frames. And then .save, which after I've called render, my stream is now a frame stream rather than an even stream. And when I save, that would give me access to things like
MP4
files,
maybe or something, right?
04d.png if I want to save a directory of PNG images, for instance. Maybe JPEG and very clearly MP4, right?
But I love the image thing. I didn't think about that. But then you can just take each packet and then dump into an image. Wonderful, yeah.
Yeah.
And then we can add some time constant, right? So we can add some kind of trailing effects and all sorts of things.
100%.
Wow.
And then you can add color maps as well. So you can actually get lovely colors. So your decay changes not just through intensity but color as well, which looks gorgeous. We can have a little bit of fun with the visualization of the information. If you have a frame stream, you could also feasibly do something like .watermark, where you're adding your little logo at the bottom of the stream, right? Why not?
Yeah, exactly. That's pretty cool. Yeah.
Or perhaps more importantly, add a time code where you show. So those are some of the features that we're using quite a lot in the other tool that I mentioned, the precursor. Some of this stuff, and especially when you're working with slow motion, you're extracting very high speed things from an event stream. Not so much to work with it quite yet, but just show that it's possible. Finding the times at which, say, when we're working with lightning recordings, for instance, finding the times at which it starts and ends by looking at just the video as an MP4, finding the time codes you care about, and then saying, well, from that point to that point, I'd like to render it again. Those are really useful features. So those things are not in it yet, but yeah, if we can get to the point where we have all of those things, I'll be very happy because I think that it's going to be very useful.
I mean, for so many things, right? It's going to save so much time. But I like that we're going there iteratively, right? So already now that you can do this crop example, you can put it into a file. Like I think that showed the value, right? That's already useful for me at least at the moment. So I think that's absolutely wonderful. I mean, now we've looked into the event stream kind of architecture and the filters. Last time we looked into the GitHub Actions, which I think is fair to say there's a bit of progress. So I guess it's fair maybe to at least stop the discussion at the moment. It doesn't mean that you, Alexander, can't keep working because there's a lot of stuff more to do. So keep following the GitHub and see what gets updated there for the viewers. But I wonder whether we can slowly maybe transition to the second guest, which is fantastic. Like I'm inundated by wonderful people here. Because I think like Faery is a wonderful example of like a tool that's very practical, right? I think it's fair to say something that a lot of PhDs have spent a lot of hours on. So if I would be a PhD and someone gave me this tool to begin with, I probably wouldn't have developed quite a few of the libraries I have been developing. So hopefully that will kind of help the ecosystem. And I'm really excited to have Peter here because Peter has shown us this amazing tiny chip, which is also fantastic. And with all respect to the Spinnaker team, I remember working with Spinnaker as a PhD student in 2019, and that also took a significant chunk of time. So if we can kind of use modern tooling and improve the software infrastructure for new chips, I think that would also be a significant contribution to the field. Peter, how have you tackled that in any way, shape, or form in your work?
Interfacing?
I mean tooling. So I know you built with Thanos, right? Or what's it called?
Talamo.
I'm so sorry about that. I should have researched that.
Thanatos, different god, different reference. So we are trying two things, I think, internally. So we're going for more standardized type tooling, building on the existing, on the mature, on the known. Like I was saying earlier, it's very important for a lot of customers to be able to know how to quickly get up to speed with a tool. And yeah, we're not a front-end website development company. We don't need to change to a new framework for JavaScript every couple of months. I don't know
That's
if that
fair.
joke is actually still relevant. I'm sorry to any front-end. Yeah,
I've done some
not
front-end
that strict.
development. That's absolutely how it is.
Yes. So we're building a lot of our tooling in Python, mostly from it's not yeah, it's building on top of PyTorch. We're not going very exotic because we know what we're trying to do and what we're. I think this is also the point a bit about Spinnaker, that um, it was a research platform. It is a research platform. It was meant to be flexible, and the design for what could be done with it was maybe not the most um, efficient, but the point was the flexibility for a lot of scientific workloads. And it's very difficult to get clear requirements from a scientific workload of what you're actually trying to do. And for us, it's slightly different because what we're trying to put as an input to a chip is sensor data. It's not arbitrary data. We're not streaming over Ethernet, over USB, over where the point is to connect right next to a sensor. So in terms of interfacing, we have the digital interfaces and we know how to drive them. In terms of how to get the software up and running, well, we've built a lot of knowledge of how the chip works, how the architecture functions, quantization, where, how, into the SDK to not be super attracted by other platforms that can do optimization for SNNs or for descriptions of SNNs like a Pine. So we don't immediately support something like Pine. I know you and me have talked about NIR in the past, and it has a few features that, or a few promises that are very nice for what we're trying to do. It's just that so there's the two sides again of neuromorphics. There's the industrial, so for us at least, it's the industrial side of creating a product that can solve sensor edge problems, applications. What are you trying to do?
I just hit myself so that you guys get more screen real estate.
Wait, no,
Right.
come back. I mean, you're already on screen, so
Yeah, exactly.
right? Okay. So the focus is the either on it's mostly on the customers and how to get them up and running with a framework that they know, that includes a lot of intelligence in the box, but it's like they're functions, classes, whatever that we know. We want this kind of regularizer, this kind of quantizer, different. We recommend the things more than say use this. So we recommend a particular kind of loss function. Use this one, not this one. This one has better performance for the kinds of stuff that we're doing.
But how
It's
many of
less
that
about
is
tuning up algorithm.
customized is my question, right? Because basically you're right, you're saying you're using PyTorch, but PyTorch doesn't really have spiking neurons, right? And I guess
Yep.
some of the loss functions and or quantization mechanisms and on so forth might not be in vanilla PyTorch. Right? Is that something you
That's fair.
bundle with Salamo then?
Yes. So that's the point. It's
Hmm.
it comes with what you need for the system that you're targeting, which is our chip. So a lot of it is pure PyTorch, but maybe repackaged a bit. Um, so loss functions, we're not repackaging anything. We're just saying you can use any of these loss functions. There is no restriction. We recommend the following because of this feature of the SNN. it's more stable. It trains better if you use particular loss functions than others. They come standard in PyTorch. You just import them from Torch. But
Okay, yeah, that makes sense. So here's kind of the architecture I pulled up on from your website. So what you're doing is you have this model description in Python, which you also do with Talamo, but Talamo is then also able to translate all this fancy Python code into the chip, like you said, into to Innatera, right?
right, it can. So you can use it for description of the network, the layer organization, the connectivity organization, the initialization strategies, whatever.
Mm-hmm.
You can then use it to optimize all the parameters by using, again, the typical classes
Optimizers,
objects that
I guess.
yeah, you just grab an optimizer off the shelf and you plug it in, and then hopefully I mean, depends a bit on the hyperparameters and everything else, but assuming that you've not done something very hideously wrong, too big learning rate, too small learning rate, whatever, you're going to see something
Right.
happening that's very
Yeah.
sensible. You can then evaluate whether you like that kind of performance and then try to deploy it to a hardware. And then on the hardware, you can run it directly with basically Talamo in the loop. You can get what the performance is on the device, and then you can deploy it. You can deploy the full application to the device and have a deployable. You have some application that you've compiled down that can say live natively on the chip, and then you can put it somewhere in the environment. You can put it in headphones to say do scene classification to figure out what kind of environment you're in. Currently I'm home. Do I really need all of my heaviest active noise cancellation settings that eat my battery? Probably not. Uh, Generic applications. We're not targeting any specific sensor agnostic.
So,
From
In
a,
principle, also image.
sorry, go ahead, Alexander.
I was wondering whether from a user perspective, it felt a bit like working with an FPGA, where you're working on in the local framework. I know that the architecture is surely very different, but more from a workflow perspective, working with simulation, once I'm happy with what the simulation is showing, I flash it to my hardware. Is it still really different in terms of feel?
That's one of the reasonable flows. It's you can treat it like an FPGA, but if you're it's I guess so. I also have a quite I working with Spinnaker, and for whomever's worked with Spinnaker, you find out that you have a few layers of abstraction. One layer of abstraction that comes in Spinnaker at the level of Pine or the graph front end is that you have something in PyTorch that describes what the operation of the system is. Spinnaker specifically doesn't do anything with that description at the level of PyTorch. It doesn't actually, as far as I remember, execute it on a host PC, which was actually a contention point for a long time for us there. So you can't use it as a simulator of what Spinnaker would do. Such a system apparently exists, but it's so far detached from the mainline Spinnaker tools that it's probably not a real thing anymore. But some sort of simulator of how Spinnaker would work exists. Assuming that, you would want to run it on a host PC. You would want to check that this will probably run correctly before you say. So in order to also do a bit of debugging, to say when I deploy to my hardware, I seem to be dropping a lot of spikes somewhere. I'm not 100% sure what the source of the backlog is, where I'm getting all of these drop packets that ruin the entire performance of my system. You don't have full observability on hardware, therefore you'd want to do it in a simulator, maybe with a cordoned off section, and maybe injecting a lot of packages and having a sort of unit test for the kinds of operations that you're trying to do. Anyway, you have a lot more control with a simulation. So the flow could be like an FPGA, but if Spinnaker has this high-level PyTorch, it also has a low-level C analogs of each of the functions that you'd implement. in PyTorch. So it has a Poisson rate encoder object that lives in PyTorch, in Python, but it's mostly a wrapper around parameters that you would inject into a templated Poisson encoder that is a C function. You give that block of C code data to be able to produce spikes, events at the correct rate. So you can also use that kind of flow. You could go much more. You can use this kind of analogy of having a high level description plus the low level implementation. But really, you can also treat it like if you go up a bit, Jens, there talk about a nimble on chip RISC-V CPU. You can also implement a lot of functions engineering wise. You can build on top of the RISC-V core and say, I have certain features that are pre-built in the SNN domain, and I'm gonna focus a lot of my effort on the embedded development on a RISC-V CPU, which is very similar to an ARM core. You go and design your application and build it and deploy it, and all fine and dandy. And you can also think from the perspective of this kind of low-level embedded engineer, firmware engineer. So you don't have to be a hardware engineer to understand the analogy about an FPGA.
I see. What sort of...
Sorry, go ahead.
Sorry, go ahead, Jens.
No, okay. So I just wanted to ask, like, because I think this is obviously amazing. I think, especially for the simulation part, you need your own, box, because obviously your chip is different from other chips, right? So to simulate and get this kind of validation data, you definitely need your own simulator. I will say though that I did a presentation recently. I think we counted in the order of 20 or more spiking neural network simulators out there that all have their own merits. And so some of them are really good at particular things. And as a PhD student who's not particularly bought into any of these platforms, I would of course love to be able to integrate these things. So the benefit of PyTorch, for instance, is that you can just take your model and run it on CPUs, GPUs, whatever, pretty much everywhere. Does any such thing exist for you guys? Like is there anywhere I can take my Norse model or as an NTorch model into Talamo or support that translation?
A translation from a different simulator to Talamo.
Well, so for instance, like you've worked with quantization. I know, for instance, SNN Torch is also great with that, right? Can I train a model using SNN Torch quantization and then dump it onto your chip or your system, basically?
Okay, working with this specific example, I would have to ask the question, to what extent can you modify or constrain the application on SNN on SNN Torch to be close to what we implement in our device?
Ooh.
What are the levels of customization that you have in the source simulator to bring it closer to what we have?
Right, so now you're talking about neuron models.
I'm talking about everything. I'm talking about any sort of, at any level in the model in the computational pipeline. There's going to be trade-offs in what you can and can't do in terms of preprocessing on device, for example.
Yes, you're also referring to the RISC-V CPU.
I'm talking about the entire pipeline.
Yeah.
So what we are trying to do is not just optimize a network, we're optimizing a pipeline.
That makes sense. Yeah.
So we care about the end effect of looking at the data stream, which is what you're also doing.
Smooth.
But the goal is to get to that endpoint, and so we care about the entire compute chain.
I mean, in this specific example, it would. Yep. No, I think it's a really good point, because this specific example, it would not be all the infrastructure, if you will, like all the platform specific handling of data I/O and so forth. That would be very specific to the network. So what happens on the analog mixed signal neuron synapse array, more or less, right?
Okay, so you're saying ignoring the rest of the processing pipeline, modeling just the bit that is related to the SNN acceleration.
Is that even meaningful for you? I mean, can I meaningfully detach the ferrying of data into the chip from the network operation and out of the chip, of course? Because I mean, my intuition goes, okay, if I have a network, right, then it's going to behave in a certain way when I kick it, right? And so it doesn't really matter who kicks it, right? It could be the specific chip here, or it could be a simulated pipeline in principle.
So in principle, if you're looking for maybe an algorithmic level solution, an algorithmic level exploration where deployment is less of a concern, you're trying to see in principle, could we get somewhere close by training SNN Torch and deploying through Talamo or something like that, then to me it sounds reasonable. You could get close. The disobeying or going over certain soft constraints or disobeying hard constraints might mean that in practice, once you actually try to deploy it on a device, you're not gonna get anything meaningful out. But maybe you can get close in a simulation that maybe doesn't have quite the same level of modeling or stops as the actual physical device. Because in order to get the actual hardware, you'd need something that is the actual hardware to see what it does.
Yeah, but is that then even meaningful? Because if you don't get great performance, then it might not even be worth it, right?
You get the ballpark. You get the beginning of, or you get close. You might get close. This is a very hypothetical scenario where it's very difficult to say whether you're going to get close or not and what the generalization performance is going to be like. But so in principle, it's possible to detach a bit the rest of the system. I have a feeling that in practice, though, you might want to take into account some of the other constraints of the system to be able to get as close as possible. I think that even in the worst case scenario, having a solution in SNN Torch means that we should also have a solution inside Talamo. So even if you were to start, for example, by doing what's it called?
Quantization? What do you mean?
No, by grabbing the weights from SNN Torch and using it as an initialization, for example, within Talamo, that would provide a reasonable direction.
Okay, yeah. So you can do like post hoc optimization based on existing architectures. Is that?
You could do a fine tuning.
Yeah.
Or,
fine tuning is, I guess that's exactly the word for it, actually. But is that something you see happening? Because for that to work, then also SNN Torch needs to have your neuron models, and I guess since you're an analog mixed signal, there's gonna be some discrepancy, right?
You'd need to know it. You'd need to know what the implementation is, yes, and be able to model it in SNN Torch.
Are you happy with that as a company who's very careful about your IP? Are you happy to release that sort of information?
Maybe I would have to, do the threatening part that I can't possibly say on a recording. But so
well done getting around that.
Tricky.
Yeah.
So it's always tricky for a couple of.
Okay. Yeah, I mean, I don't want to put you on the spot, because I think it's a very interesting problem, actually, because you have some really interesting tech here, right? Which is obviously not something you want to give to anyone because it's a solution. At the same time, right, I also sense that there's an interest in integrating with the existing ecosystem, right? Because ideally, you can take a lot of the existing models and just dump it on your chip and then show, oh, this just works 10 times or 100 times or 1,000 times better than anything else, right?
Then that is a very reasonable direction. That's why I am very curious about how this can integrate and how we could use it. How NIR could integrate. How maybe at this point even ferry data to our chip and maybe run on that nimble on-chip RISC-V CPU. Whether, I mean, eventually, if you decide that maybe NumPy is not the thing that you're looking for, it's not GPUs that you're trying to accelerate the operations for, but maybe an embedded MCU.
So let me just
brings us closely to NIR. Okay.
show a few things. Well, because you mentioned it, right? I mean, and we've talked about this neuromorphic intermediate representation, and I'm a little jaded or biased here, I would say, because yeah, I've been working on this, and I think just briefly, right, the interesting thought here is that NIR is supposed to be like this intermediate between different simulators, right? I just wanted to preface that for the viewers, but what I really wanted to ask you actually, Peter, is if you go to the Open Neuromorphic Hacking Hours website, where we've closed like a ton of issues, and we're very proud of this, and Faery is going to be on the list very soon. Like, I'm actually curious, as you as a company, here are some example of projects that we in this open neuromorphic space are developing, right? Are there anything you would like to work with? So NIR being one of them. Like, is there something you would like to hack on in this session, for instance, that might benefit you? Bop, bop, bop. I can maybe go through the projects if that's helpful.
Yeah, go for it.
So A-Stream is one instance of this address event streaming, which is mostly focusing on C++ and GPU code. Faery is then, I think, the spiritual successor of both Alexandre's and my work. So we'll also support, I think, some of the GPU things here. NIR is this neuromorphic intermediate representation you saw before. Norse is a spiky neural network I've been one of the developers for, which is yet another one of these SNN simulators. And Spix, or Spikes, I guess, is then a JAX-based, yet another spiky neural network simulators. So all of these projects have open issues, and these issues are just the subsets where that's been marked with help wanted. So just a curated list of issues where that should be accessible and where help is more than welcome. So, for instance, for NIR, right, there are some wrong dependencies in the notebooks, and more example code in the documentation is needed. I think in general the documentation for NIR could use a refresher.
So I think that some prioritization is required. Overall, everything is interesting, but some things are maybe more immediately useful than others.
I like useful.
Sorry?
I like useful. I mean, it should be useful. Also, not just for others, but also for you, right? The whole point is that we build something which we can work with. Right?
So I think NIR is up there on the list of having something that isn't maybe a replacement for Onyx that everyone can get behind. I think would be fantastic. So
let's explore that. That's awesome. And I just want to go into the issues, and then you can see that there are more issues than that, but you can see these two are then listed with help wanted.
So I think the bits that are useful in the order of operations here, at least for anyone trying to get into NIR, my feeling is that starting with the documentation, reading it is essential, and therefore starting with the help wanted for how to generate the documentation is also useful. You get exposed directly to not the doing bits, but how to do bits.
Yeah. That's the next important. So we can just go through how the documentation is created, and maybe.
And then explain how it's what the documentation is supposed to. What is the documentation? What is NIR supposed to do? How is it supposed to do it? While doing it, because we're going through. I mean, notebook docs run with wrong dependencies. Kind of vague for me. I don't know exactly what could possibly be the cause, but that brings me closer to actually seeing the documentation, therefore understanding what NIR is doing.
You mean this one? So.
I mean, example code and documentation. I think upload example code in the documentation.
So that's because we have some different
example
simulators.
code is even better.
Right, and there are some of them are missing code. But yeah, that's a great point. Are you familiar with Visual Studio Code sharing sessions?
In principle, I know some of my colleagues have been using it, but I've not had the chance to really do a lot of pair programming recently on account of different types of work that have to be
I like it a lot because then we can actually go around, and ideally also I can follow your cursor because then I can see what you're working on and thinking about. Yeah.
But yes.
Peter.
Hard stop at 6? Question mark.
I was just about to say I have to run in 10 minutes, which is very unfortunate. So I was thinking about how we can strategize this. Maybe it makes sense just to talk about NIR for the next 5-7 minutes, and then maybe set it up for another session, and then maybe round off with some general remarks. What do you guys think?
That sounds very appropriate for 10 minutes.
Because it would be awesome to start working with it. I'm even happy to go through some of the code bits, because it would be fun to, like you said, empower people to work with the documentations, because the documentations are actually just markdown files, they're text files. It's very straightforward to work with, except, sorry?
I wasn't expecting anything else.
Well, except some of the examples which are actually built also as notebooks, so Jupyter notebooks, where you then run Jupyter code, and that's one of the issues, because some of the Jupyter notebooks are failing because they just need to be updated. But most of the files are just marked down. So here are just descriptions of what it is, and I think this diagram's
Are they failing because of NIR as something that sits in between a lot of different software platforms, each one having a different roadmap, a different update cycle? They'll obviously become out of sync with each other probably quite quickly. Is that fair to assume?
Well, I mean, so I think right now the error here, for instance, in the lava, has to do with some dependencies not resolving properly. And I think one of the challenges for NIR is that we're kind of bootstrapping things as we went along. So because we have to build NIR as a dependency for other libraries, right? But the libraries needed to depend on NIR to be able to use it. So it's kind of this circular thing. And I think this worked really well on our own machines when we had all these dependencies correctly set up. But as soon as you propagate this to production and run it on the official library versions, then something crashed. That's kind of my interpretation of it. So I think this issue just means to say some of the Python code we wrote for the examples don't work because it uses both. Yeah, there's some dependence clash here.
Right. So how is this meant to be managed at the moment as a process? What is the protocol for NIR to say we support Lava version 5.3.1 versus 5.3.2?
So that's an excellent
evaluation, and whose side of the evaluation? Who's doing the evaluation? The Lava
That's-
side or the NIR side?
Yeah, so that's a wonderful point. NIR isn't supporting anything in principle, right? And there's a caveat to that, because NIR has some primitives, right? And NIR's built up about some computational principles. And I guess that's also why it's reasonably interesting for you guys, because those primitives are continuous in time, they're not discrete in time. So they're describing differential equations. Now, the idea is that NIR just declares these. NIR has no computation, right? There's no place in NIR where we define or we compute an affine transformation, but we declare them. So NIR is just it's a dictionary, if you will, where you can map layers to their parameters. So you can say you have an affine, and that affine is parameterized with weights and biases. Or you have a leaky integrator, and like leaky integrator is parameterized by this and this time constant, and so on and so forth. So to your question, how then does NIR support, let's say, Lava? And I would say it's the other way around. Like it's this lava that's supposed to say, okay, we have a mapping. We know what our leaky integrator corresponds to in NIR. So I'm going to build that mapping. I'm going to build that translation that takes this certain primitive in lava into NIR. And you can even technically go the other way around, right? So you can take a NIR, like a lava primitive into NIR, or a NIR primitive into lava. And the reason for that, sorry?
Would you expect that the list of primitives here is complete?
No.
How do you
No.
define? You're right. So
And
you
that's the caveat. So this will have to be
new
updated.
primitives.
So for instance, let's say we were to support another chip, let's say Innatera's T1, right? And you'd need a new primitive. Then that would have to be added to the list of NIR primitives. And you might wonder, what does that do for all the other libraries? Well, then all the other libraries need to get up to speed. So all the other libraries need to then implement a translation to that primitive. The reason why this worked really well for neuromorphic libraries here is that everyone knows what a leaky integrator is, and everyone knows what a leaky integrated fire primitive is. So those exist. So building the mapping into, say, Pine or Spinnaker 2 or something else works really, really well because it's already implemented. It'll be Sorry, go ahead.
I'm wondering whether there is versioning in NIR. Are we looking at NIR 1.0, and would there be a NIR 1.2 at some point where you add some of those primitives and you can say, I implement NIR 1.1 and libraries need to deal with that?
That's exactly the thought, right? So you'd be able to represent things at a certain moment. So we have every single NIR graph is essentially just a blob. So we can store them in Python objects or in HDF5 files, and they're all tagged with a certain version. So we know exactly what we support.
That's already the case. Like this list of primitives has implicitly a version.
That's correct. And I mean, let me put it this way: all the graphs at the moment have versions very explicitly. We haven't written it on the website because NIR isn't version 1, so we haven't had the need to integrate more primitives. But the wonderful idea I think about this flexibility is that when you add a new primitive, none of the previous mappings or previous supports will break, right? It just means that nobody else supports your primitive. So there's a bit of groundwork to be done to then add mappings to additional primitives. One of the benefits of this collaboration, and the reason why we have more than 11 platforms that now support NIR, is that most of the people in the paper actually develops these platforms, right? So if we have a direct line to those platforms, it's easier to proliferate and spread these primitives. But that's indeed an organizational pain point, right? We will have to manage that later. Yep. But that is the core thought, right? So that you can do all this mapping by yourself. Like, Tanamo can sit down and support mappings from other libraries, but they have to do them one by one, right? So if you have some software libraries here and some hardware libraries here, you'd have to have an n by m mapping, but with an intermediate representation, a bit like on and x and so on and so forth, you might only have to do one.
Yeah, that's clear. It's a good feature to have.
So, I mean, what I'd be interested in with T1, right? And I recognize we don't solve that tonight. Is whether some of the network components can be described in this formalism, whether we can define some kind of primitive. And the reason for that would be that you can then interact with the ecosystem, right? So you can use some of the toolings and the processes in some of the other libraries. But of course, it requires a description of the primitive, right? You'd have to figure out what the dynamics are.
Yeah, that's very clear. And you'd write that down in what form?
So
how do you describe
we just literally, like, we published a paper with this, right? But literally, the only content of our code is Python data classes. So you can see here, for instance, we have a few. Let's just take the linearity here. it's literally just a set. It's a tuple, if you will. It's just a set of elements. There's some weights, there's some biases, and then we have some metadata and type information.
But
But
how does it get? Okay, go on.
but the equation itself is implicit. This is just the declaration.
Right. And on the other end, you'd have to define some sort of reader of a what? A JSON, a custom format.
So NIR implements this for you. So NIR is basically a file format. You can put this into an NTF5 file. But we also have just Python objects. So the NIR basic library allows you to do either transfer bytes over some channel or just work directly with Python objects. So you can see, it's an example I'm familiar with, right? You can see here in Norse, I can take a network and load it in from NIR, for instance.
Mm-hmm.
Or I can take a NIR model and then using a serialization write that into a file. So that's it, basically.
Fantastic. And the execution details?
Well, that's exactly specified by, so in this case, Norse. So this NIR graph doesn't specify anything else than a dynamics, which is implicit in the object, if you will, and the parameterization of that dynamics. So that's really all we have. But the whole idea is that NIR is not opinionated about the evaluation. It just declares the dynamics, and then it's up to you to implement that as a platform. And that's the crucial part, right? Because if the dynamics in Norse is very different than the dynamics in Talamo or in your chip, then you get very poor results when you try to transfer parameters from one to the other.
That is very clear. But also somewhat important, but like what I was saying earlier, is that we're concerned with full computational pipelines that we are.
Yeah.
That you're trying to solve an entire problem, and the description that's in front of me leaves out a few details that you'd either have to transfer orally or from a source in text that says you need to run with these other settings.
Yeah.
The network with these other settings. And
Yeah.
between this, how it was trained, it was generated. This description was generated by blank procedure that you would have to obey if you're trying to go and embed this flow, the embed components before and after the neural network.
Yeah.
Otherwise, you can't make the magic work.
Yeah, that's completely correct. I mean, NIR only describes, you can call it a function, right? It's a black box function. You give it some input and it will give you some output. There's nothing about platform-specific details or, all the details you mentioned. There's a metadata thing, but that's everything. That's all you can, right? So here you can embed stuff into the metadata format, but the whole point is actually to avoid platform-specific details, right? That said, I'd love to continue the talk to find out. I mean, NIR doesn't have to. I don't think NIR is the end-all, be-all of all neural network exchange formats, right? I think it's useful for a lot of the neuromorphic platforms, but it leaves out all these details, the logistics that you mentioned. So I'd love to continue talking, maybe in another session, about how that can be addressed, and ideally also open source, right? Because then everyone can benefit.
What do you mean open source? I thought the NIR is.
NIR is open source, but NIR is not dealing with all the logistics you talked about.
Right.
But I sense that's kind of a separate problem, right? Because I mean, even though it's going to be hard to translate it because that doesn't also SNN Torch doesn't have an understanding of that implementation either, right?
Quite right. I think a lot of I believe that a lot of other platforms deal with less with this problem that we have of needing the entire description, of having the entire description and worrying about the entire compute chain.
This may also prove.
Sorry?
This may prove to be a commercial challenge depending on what the core business model of neuromorphic companies ends up being. a little like what Apple tried to do in the early 2000s, where they were trying to lock in their software. Because really, they were a hardware company, but their software was good. So what they were selling is the whole package. And on purpose, we're designing the software not to be compatible with anything else in terms of hardware and vice versa. So if what ends up being the most valuable is the hardware, then NIR is going to be amazing. It's how you let someone else do the software and everything moves all over the place. And what you focus on, what you get right, is the hardware accelerator. However, if the key added value of some companies ends up being selling a solution where it's not so much about the hardware in and of itself, it's about here's a whole framework. You download this thing, you open a cool software, you move things about, you load your data, it trains it, and it's ready to go. The chip isn't necessarily all that much better than the competition. What's much better is the whole experience. Then NIR might get in the way of that because it's like, I don't want others to benefit from my cool pipeline. I want to make sure that it's not compatible with NIR because they might otherwise use that core model on another chip, right? I certainly hope that's not going to be the case. But that might be worth factoring in some of those discussions if, we're talking about not just an academic context, but also a commercial one.
I'd love to see what your answer to that, Peter.
I think we're
No
over
pressure.
time.
And actually, we are. I will have to run, but of course, the friendly banter doesn't have to stop with me leaving. I just want to also, for the viewers, thank you guys so much. Like, it's so incredibly. I'm so incredibly grateful to be joined by so much expertise. I mean, both you, Peter, and you, Alexandre, have been like foundational for the work in your field. So I'm just having a lot of fun with this, and I really hope we can continue in the coming weeks. But thank you so much both for taking a chunk out of your calendar.
Thank you for
so
hosting
much. It
this.
was fun.